Dr. Sonika Singh is PhD from Motilal Nehru National Institute of Technology, Allahabad. In 2020, she completed her PhD in the area of cryptography. She also completed her MSc and MPhil in mathematics from CCS University, Meerut. She has published 7 research papers in peer-reviewed journals. She has participated and presented papers in several conferences and workshops also. She was invited for delivering the talks in workshops and 2 international conferences. That's very good. She qualified CSIR NET in 2014 and GATE in 2014 and 15. She received the Best Paper Award in NetCrypt 2019. So let's welcome Dr. Sonika Singh to our 8th SOAWAL webinar. So Dr. Sonika Singh, you can start your talk now. Thank you.
Thank you so much, ma'am. And thank you, everyone. Ma'am, may I off this camera, please? Actually, I am in 2 devices, mobile and laptop also.
As you feel comfortable, accordingly you can do.
Okay. Thank you so much, ma'am. Okay. Good morning, everyone. Myself, Dr. Sonika Singh. I'm here for talking about applications of mathematics in secure communications. We all know about some very basic mathematical concepts like prime numbers, co-prime numbers, congruence, modulo relation, groups, vector spaces, etc. So I will talk how can we use all these concepts to secure our communication. So before going to application part, we should know what do we understand by communication. So communication is a way for exchanging our thoughts, our information, our data to each other, and we can see our secure communication by the term cryptography. The cryptography is nothing but an art of secret writing and hiding informations. Suppose we are talking to each other and the third person is listening and observing all the talks of us. Even then, if he or she cannot understand about what is being said between us, then this is called cryptographic way to talk each other, to interact each other, to communicate each other. So in cryptography, just we are hiding our data, our information to the third person. Even then, he is with us, he is listening us, he is understanding us, what is going on. He is all observing. But the single thing is he cannot understand what is doing between us, what is happening between us, what we are saying to each other, what we are exchanging with each other. So this is called cryptography and this is called secure communication. Okay, so in cryptography there are some terms like plain text. Suppose plain text is the original message which can be readable or understandable by anyone. And in cryptography, we are hiding our information. That means we are hiding our plain text. And the hidden message is called ciphertext. And the process by which we are hiding our plain text to ciphertext, into ciphertext, that process or that rule or that functioning is called as encryption. And the reverse process, that means to get plain text from the ciphertext, to get original message from the hidden message is called decryption. And the thing by which we are going to do all to both of these process, encryption and decryption, that word, that term is called key. For example, like we are going outside of our house and usually we lock our house. Why? To protect our house, to protect our things, to protect our all the price list things. Okay, and what we do after returning home, we unlock that lock with the help of key and we can go inside the room, we can go inside the house. So in the same way cryptography works, we lock our message and then we unlock our message with the help of key. When our message is unlocked, it is called plain text. When our message is locked, it is called ciphertext. Okay, so based on the type of key, we can categorize cryptography in the 2 types. First one is symmetric key cryptography. If the encryption and decryption keys are same, then we call it symmetric key cryptography. If we are using the same key to lock and unlock both, then it is called symmetric key cryptography. And if we are using encryption key and decryption key are different, that means we are locking with some another key and we are unlocking with another key, then it is called public key cryptography. The key which is used for locking, it is called encryption key, and the key which is used for unlocking, it is called private key or secret key. So this is called symmetric when encryption and decryption are same with the help of a single key, that is called secret key. In the symmetric key or classical cryptography, key is called secret key. But in the public key cryptography, keys are different. Encryption key is different to decryption key. Key is called public key and decryption key is called private key. So let's come to the some basic mathematical concepts which can be used for secure communications. Okay, so these concepts like prime numbers, co-prime numbers, Euler-Phi function, congruence modulo relation, inverse modulo relation, Euler's theorem, group and cyclic group, vector spaces, etc., and many more are there. Ring, group, field. There are many more. And in last, we can see the application part of these mathematical concepts. That's how can these all mathematical concepts can be used to secure our communication. And these security, I will talk in terms of some crypto systems, some cryptographic designs like Rsa Crypto System, Algorithmic Crypto System, or some classical Caesar cipher, etc. So let's start with the prime numbers. Prime numbers and co-prime numbers. The initial very basic concept of mathematics. A prime is nothing but a prime number is that which is divisible only by itself and one. And if two numbers are having their common factor, their greatest common factor, their greatest common divisor is one, they are called relatively prime numbers or co-prime numbers. And with the help of prime numbers, we can define Euler-Phi function. Euler-Phi function is nothing but, suppose we are going to compute the value of an integer n, Euler-Phi value of n. So we will take those value which are not exceeding n and relatively prime to n. Suppose I am having my number 10 and I want to compute phi 10, Euler-Phi value of 10. So I will consider only those positive integers which are less than n and relatively prime to 10. Okay, so we can see here phi 1, the Euler-Phi value of 1 is 1, and if we are having our number is prime, then phi p, the Euler-Phi value of p is p minus 1, and if we are having our number is composite, so we can factorize it into prime factors. Suppose prime factors are m cross n, so our Euler-Phi value will be phi m into phi m. And suppose number is in terms of p to the power e, then phi p e is equal to p to the power e minus p to the power e minus 1. And if something like n is p1 to the power e1 cross p to the power e2 cross k to the power ek, then phi n will be p1 to the power e1 minus p1 to the power e1 minus 1, and so on. If n is easy to factorize, then phi n is very easy to compute. And if n is difficult to factorize, the difficulty of finding phi n is simply based on factorization of n. For example, suppose we want to get the value of phi 240, then we will simply factorize it into the prime factors, prime powers, and we can get phi 240 is 64. And suppose we want to get the number of elements in Z14 star, it is simply 514, and the numbers are 6. We can see the numbers are 1, 3, 5, 9, 11, 13, which are less than 14 and relatively prime to 14. And there is one interesting point. If we are having n is greater than 2, the value of phi n is always even. Okay, the next mathematical concept is congruence modulo relation. If A and B are having...
Madam, excuse me. The phi of Mn is phi m into phi n when GCD of Mn is 1, na?
Yes, sir. GCD of Mn is 1 because we are taking Mn is prime factorization of n. M is
Right.
prime as well as n is prime.
Okay.
Okay, sir.
Wait, M may not be prime, na?
Yes, sir.
M and N, whether both are prime,
Both are
not
prime,
required,
sir.
no?
Both are prime. Because sir, to get the value of phi n, we first factorize n into prime factorization.
No, ma'am. If M and N are simply relatively prime, they can then phi
There
M
can
n
be,
is
yes.
simply phi M and phi N. They
Yes.
need not to be prime, M and N both.
They need not to be prime.
Simply the GCD has to be 1. That's it.
Exactly. If GCD of Mn is 1, then phi of Mn can be written as phi
Yes,
m into phi n.
yes. Both M and N can be composite also.
Exactly. Because otherwise phi of 36 we cannot find out. Na? Okay, madam. Carry on, carry on.
Okay, sir. Okay, so the congruence modular relation is if A and B are having same remainder after dividing by n, then it is called A is congruent to B mod n. For example, we can see here 103 is 3 mod 10. 103 is congruent to 3 under mod 10. And we can see it in the terms of addition modulo and multiplication modulo. In addition modulo, we will consider, if we are taking modulo n, we will consider 0 to n numbers. And if we are taking multiplication modulo n, we will consider it 1 to n. That means the GCD of x with n should be 1. A cross B mod n. Okay, the next one is inverse modular relation. If we are having AB is congruent 1 mod n, that in that case we can say that B is the inverse of A under modulus n and A is the inverse of B under modulus n. And inverse only exists when GCD of A and B is 1. For example, if we are taking n is 26, A is 7, then we can see here 15 is the multiplicative inverse of 7 under modulo 26. So the next theorem, next result is Euler's theorem with the help of Euler phi function. It is having two versions. First version is if A and N are coprime, then A to the power phi n is congruent to 1 mod n. And the second version is if we are having A to the power k phi n plus 1 is congruent to A mod n. By multiplying with A on both sides, we can get second version of Euler's theorem. And this second version of Euler's theorem will be used in Rsa Crypto System, our main crypto system. So with the help of Euler's second theorem, we can get multiplicative inverse under modulo a composite. That is A inverse mod n, where n is a composite number. We can get it as A to the power phi n minus 1 mod n. It will be the A inverse under modulo n. So my next concept is group and cyclic group. Suppose we are having a set with a binary operation addition. Suppose it is called a group if it is satisfied with a closure property, associative property, identity, additive identity, additive inverse, and suppose if it is commutative also. If only 4 properties are there, closure, associative, identity, inverse, it is only group. And if it is satisfied commutative also, then it is called abelian group. And the next concept I am going to use in our crypto system, that is cyclic group. That means if a group, if in a group G there is of that group can be expressed as a to the power n for some integer n, then we can G is a cyclic group generated by that particular element A, and that particular element A is called generator of that group, and order of cyclic group is equal to order of its generator A. So the next is vector spaces. We will use it. Vector spaces are set V, set of vectors with two operations, vector addition and scalar multiplications. And there are some axioms like closure property with respect to addition, commutative property with respect to addition, associativity, identity, and inverse with respect to addition. That means abelian group with respect to addition, and scalar multiplication. CU in closed with scalar multiplication, and distributive property. Cu plus V is equal to Cu plus Cv, and CDU is equal to CDU. 1U is equal to U, multiplicative identity. If all these conditions are satisfied, then V is set to be vector space over a field F, where field is the scalar quantity, from where we are taking scalar quantity. So the V is called a vector space. Okay, let's come to our main part. Actually, these mathematical concepts and many more are there we can use into the cryptography. And we will start by classical crypto system. And here classical crypto system includes symmetric key cryptography and public key cryptography. And classical means here This cryptography can be implemented, can be used by classical computers. As in classical computers, we can transfer our data into the terms of bits 0 and 1. Okay, so the first one is I'm going to describe symmetric crypto systems like shift cipher, affine cipher, substitution cipher. So shift cipher, the basic idea was generated by the Caesar's concept. The Julius Caesar, the Caesar's cipher is named after Julius Caesar, who according to Suetonius used it with a shift of 3 when encrypting, like A becoming D, B becoming E, etc., to protect messages of military significance. So first of all, shift cipher was used by Julius Caesar, taking 3 shifts. As we are having our alphabetical terms A, B, C, D, E, F, G, H, I, J, K, N. So our message space, key space, or ciphertext space is 0, 1 to 25. A is denoted by 0, 0, B is denoted by 0, 1, C is denoted by 0, 2, and as well. So on. Okay, so what did the Julius Caesar in their force to protect their message? He encrypted his message by shifting 3 letters. Suppose his message is A, so he did what he did. A becoming D, he shifted A to D, D to E, F, G, D to G, like that. So shift cipher is a particular case of shift cipher. In shift cipher, we just shift letters by the key number. Suppose key is 7, we will just shift our message to the 7 positions ahead in alphabets. So the R key space is 0, 1 to 25. We can choose any key, we can choose any message, we can choose any key number, and just in encryption, just we substitute any letter by 1 occurring k positions ahead in the alphabet. And in decryption, we do the reverse part, k position back. So the shift cipher, like for example, I'm going to talk about Caesar cipher. Suppose our plain text A B C D E X Y A B C D X Y Z. So ciphertext will be simply A to D, B to E, C to F, X to A, B, Y to B, Z to C. Suppose our plain text is I came, I saw, I concurred. So I will become L after 3 shifting. C will become F after 3 shifting. A will become D. M will become P. And similarly, from ciphertext to plain text, L will become I, F will become C, D will become A. We can see another example. Suppose our plain text is example, our original message is example, and our key point is 2. So just we shift E by 2 positions and we'll get G, X will become Z, A will become C, and so on. If your key point is 3, then example will become HADPTOH. And if key point is 3, cold will become frog, like that. Suppose another example, we are having our ATM pin and we want to protect our pin 1279, and we are using key point 3 and some extra protection using modulo n. So with using key point 3, 1279 become 4502. Like 1 is shifted by 3 will become 4, 2 is shifted by 3 will become 5, using modulo 10 also. 7 plus 3, 10, and 10 modulo 10 is 0. So 7 becomes 0. 9 plus 3 become 12, and with modulo 10 it will become 2. So 9 become 2. So in this way, 1279 with shift cipher with the key point 3 will become 4502. So it is the first example of modulo system. Okay, next is affine cipher. In affine cipher, as we know, affine like linear type of relation. So the key space is having ordered pairs AB, such that AB from Z26, because our plain text space is alphabets. So we will take from Z26, and A is such that GCD of A and 26 is 1, because we will need A inverse in decryption processor. That's why our key space is having the ordered pairs AB, such that A and 26 are having GCD 1. So in encryption, our encryption equation is EABX is equal to AX plus B mod 26. And simply decryption is, suppose EABX is Y, AX plus B is, mod 26 is Y, then decryption That means X will be computed by A inverse multiplied by Y minus B mod 26. So this is another example of modulo relation. Inverse, finding inverse also, Euler theorem second version. We can see here an example. Suppose A is 3, B is 5. So our encryption equation will be 3x plus 5 mod 26. And suppose our plaintext message is DP. And in 00 to 26, 25 coding scheme, D will become 03, P will become 15. So with the key 35, our encrypted message of D will become O, because 3 x, that means 3 into 3 plus 5 mod 26 will become 14, and 3 into 15 plus 5 will become 24 under modulo 26, and 14 is O, 24 is Y. So the ciphertext is OY. Next one is, these two examples are from classical crypto system, symmetric key crypto system, and due to time constraint, we will consider only these two. And next, I will talk about public key crypto systems. That means encryption key and decryption key are different, because in symmetric key crypto systems, key management is very typical task. Suppose I am here, and suppose you are in California or US or America, or physically very far. Okay, so how can we exchange our keys that we will use same key? So in that case, to overcome with this drawback, public key cryptography, the concept of public key cryptography came into existence. So the first crypto system with the public key cryptography is Rsa Crypto System. It is the most common public key algorithm and most famous also. It is named after its inventors, Rivest, Samir, and Edelman. It is basically based on a very hard mathematical problem, integer factorization problem. In this problem, we are given a number n, and we have to find out prime factorization of n. It is seems very simple in this statement, but if we are taking very large numbers, it is very difficult to compute the prime factorization of n, and it is even if we are using so many thousands of supercomputers, even then it is not computable in feasible time. That's why it is called hard mathematical problem. And based over these problem, RSA crypto system is based. And in each crypto systems, there are three processes. First of all, key generation, second encryption, and third decryption. So let's see the process. And before going to the process, here are 2 points. RSA uses two algebraic structures, ring and group. And in RSA, I will discuss En is the public key and teaser. T is the private key. Okay, and P and Q must be at least 512 bits. Okay, fine. So this is the key generation algorithm for RSA. First of all, we select two large prime numbers, P and Q, very large prime numbers, and we calculate multiplication of both, and we call it n. So n is P into Q. P and Q are prime numbers. Then we select integer d such that GCD of phi d and n is 1, because we will be needed finding inverse under modulus phi n. That's why we calculate E is D inverse mod phi n. Okay, fine. N is our P cross Q, A is our D inverse mod phi n, D is a random integer selecting by S, and there is some restriction on D such that GCD of phi D and N should be 1. Okay, so after selecting and computing E and D, we can publish our public key and private key. En is public key, E is D inverse, N is P cross Q, and private key is phi n and D. So we will keep private phi n and D, and we can give En to anyone. Okay, so next process is encryption process. If we are having a plain text M, which is less than n, plain text is coming from Z. Okay, to get ciphertext, we just simply do m to the power e mod n. We are already having e, which is D inverse mod phi n. We compute m, which is our plain text, m to the power e mod n. And in decryption part, we simply get back m by c to the power d mod n. Okay, We can see example here. We are choosing 512 bits P and Q. We calculate N by P cross Q. Then we calculate phi N, which is P minus 1, Q minus 1, because P and Q are prime. And it will be 309 digits. Then we compute E and D. E is 35535. D is E inverse mod phi N. Then suppose our plain text is, this is a test. So in 00 to 25 encoding scheme, 26 is the space character. T is 19. H is 07. I is 08. S is 18. And then space after this. So we will include 26 as the space character. And so on. Is a test is 0818 and so on. So this is a test becomes numerical value plain text P is equal to 190708 like that. So this is our plain text. Okay. So we can get our ciphertext C by P to the power E. So this will be C, this whole large number on the screen. And after reversing this process, C to the power D will become plain text, original plain text. And we can convert this numerical value into our plain text. 19 is 40, 07 is 4H. And in this way, we can see the Rsa crypto system's mechanism. Next crypto system is algorithmic crypto system. Algorithmic crypto system is again based on a hard mathematical problem that is called discrete logarithmic problem. And is in this problem, we are given a prime P, a generator G of ZP star, and an element beta of ZP star. These are given P, G, and beta. And we just have to find out G to the power X is equal to beta mod P and the random exponent X. We are only concerned about X because G is already we have, beta is already we have, P is already we have. Just to find out the value of X, this is called discrete logarithmic problem. Because to find out the value of X, we will have to take the logarithmic on both sides. So this is a logarithmic problem. And because our inputs are coming from ZP star, integers, that's why it is discrete structure. And the whole name is discrete log problem. This is also very hard problem. Even using thousands of lakhs of supercomputers, if we are using sufficient large inputs are P and G and beta, it is very hard to solve. It is very hard to get the value of X. That's why it is considered as the hard problem. And the cryptographers constructed crypto systems, their designs on using this problem. So this is the algorithmic crypto systems. In key generation, first of all P, very large prime, then even primitive root or generator of ZP star, then D, selecting D, and computing E2 is even to the power D mod P. So we are having P, even D, and E2. So here D is our private key and even E2 EP, even E2P is our public key. We can give it to anyone, sender or receiver. Okay. So the sender is using public key to encrypt the message. Suppose message is plain text P. So to get the ciphertext, first of all the sender compute C1, which is by equation E to the power R modulo P. And next C2, which is E to the power R cross P modulo P. And the whole pair C1, C2 is considered as the ciphertext. Sender will send it to the receiver. And because receiver has the private key D to decrypt the plain text message, sender, what will sender do? C2 cross C1 to the power D whole inverse mod P. And if we are going to simplify this, it will simply equal to P. So with this process, sender get the ciphertext and receiver gets the original plain text. Okay. So this is algorithmic crypto system. We can see this is example. And one thing is there, we are using very large numbers. In that case only, these problems are hard problems. Okay, not in case of toy examples or not in case of small numbers. So these are P, E1, D, E2, P are C1, C2, and final Bob is the receiver. So he can get the final plain text P. So these are two public key crypto systems. Okay, next come to one more mathematical concept, lattices. And why do we need here? Because symmetric key crypto systems and public key crypto systems are using classical computers. Classical computers using data in 0-1 form. And if we are using classical computers, there is no algorithm that can solve integer factorization or discrete log problem into polynomial time. But before some time, the concept of quantum computers came into existence. Quantum computers uses its data into qubit form, not in bits form, not in 0-1 form. It uses data in quantum packets, superposition of 0-1 and 1-0. Okay, and there is a mathematician named as P.W. Shor. He developed an algorithm which can solve all RSA problem, all algorithm problem, all classical problems very easily, very feasible time. So in that case, if we are having access to quantum computers, IBM company just launched quantum computers, maybe 57 qubit quantum computers, or maybe more. Okay, so if we are having access to quantum computers, the current cryptography, the current protection of our computers, of our all everything, cryptography is in everything in our daily life. All things are dead, all things are finished. So in that case, what we should do? So the mathematicians and cryptographers developed cryptography named as post-quantum cryptography that can deal with the quantum computers also, that can secure our data, our information into the world of quantum computers also. And there is a conjecture given by a computer scientist Bernstein. According to that conjecture, lattices can withstand with quantum attacks. So if we are using lattices in our crypto systems, in our designs, we can make sure we can save our data from quantum computers attack. So that's why the lattices and the crypto system based on lattices are used to secure data in quantum computers world. So basically, what are the lattices? A lattice is a discrete additive subgroup of Rn. If we are having a basis having vectors v1, v2, vn, then the set of all linear integer combinations, set of all integer linear combination of the basis vector is called lattice. B is the basis vector. It can be represented by m cross n matrix, and if we are having m is equal to n, we can call it full rank lattice. And lattice is physically we can see it like that. These are lattice point, and this is the unit cell. Gray shaded region is the unit cell of lattice. Lattices can be seen as every solid thing like crystal. You can imagine by this figure. And mathematically, these are set of all integer linear combination of its basis vectors. Okay. And there is a crypto system named as NTR crypto system. This is the most efficient crypto systems given by cryptographers Hofstein, Pfeiffer, and Silverman. This is NTR crypto systems. NTRU is basically for nth truncated ring polynomial unit. It uses polynomial ring. It uses truncated polynomials. It uses convolution multiplications. So I am not going to discuss in detail due to time constraint. Okay, so we can see the real-time uses of RSA crypto systems we have discussed. So RSA crypto system can be seen in a range of web browsers, email, VPNs, and other communication channels. So if we are using laptops, in our address bar, we are having a small lock is there. So if you are going to click on that lock, you can get all the site information, all the certificate information. You can get all the information, how your data is secure, how your laptop data is secure. And obviously lattice based crypto system is NTR crypto system, and it is used where the storage, we are having lack of storage, like mobile devices, smart card, mobile portable devices. It is recommended for embedded systems, and it is used in Goldberg chat messenger. Firstly, we can see cryptography in daily life, like electronic commerce, cash withdrawal from an ATM, chip-based ATM cards, digital currencies, computer password, military communications, pay TV, email and file storage using pretty good privacy, secure web browsing, GSM mobile phone. Like we are going to withdraw our cash from an ATM, we can see on the screen our pin is in star form. It is in encrypted form. It is not in 1279. It is star, 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 star. We input our data in our original form, and that data is transferred into its machine language, that is star, star, star. And that machine language is in encrypted form. We are going to include our data in text message. Suppose this is a test, is our plain text. So we are typing this is a test. But in computer, it will be converted into 010101 in bits form. And in cryptography, it is converted into encrypted form, we can say. And it is traveled, and after reaching to the authorized user, he can get his original plain text. So in military communications, just like I said, Caesar cipher, computer password, we are having all protected data, encrypted data, digital currencies, chip-based payment cards like ATM, credit card, pay TV like Netflix, Amazon. These are having our data, our card details also, but with security, secure web browsing, and in mobile phones. Everywhere you can see cryptography in daily life. And cryptography is the combination of mathematics and computer science. So, without mathematics, cryptography cannot be deal, and computer science also. So, this is all. Actually, there are many more concepts, but I thought 45 minutes are there. So, I am having.
Any question?
Ma'am, I am having one question.
Yes,
comment?
sure.
Yeah. So basically, you are doing encryption and decryption, right?
Yes, yes, sir.
So that is decryption is inverse mapping of a relation, is it?
Sir, we
Yes.
can say, but not exactly like that, because in symmetric key cryptography, you can say that encryption key and decryption key are in inverse relation mode, but in public key cryptography, it is not like that. You can say the process is reverse process, not inverse.
Okay.
Yeah.
Okay. So I was carefully watching that, like somewhere you have
Yes, sir.
taken suppose e to the power minus 1 something something. So is it inverse or reverse possible all the time during
Okay, sir.
decryption?
So you are saying, like, I think about a fine cipher where I used key AB. Is it?
Okay. Yes, yes, yes.
So, sir, in that case, key should be we will use A inverse in decryption process. So, sir, the process is different.
Hmm.
Again, I think you are in confusion. It is not inverse of each other. Inverse, we can say
Okay.
in only mathematical concept, but
Yes.
we are using cryptography in present time or in real life. So we can say encryption is the reverse process of decryption. In that sense, only plain text is plain text from ciphertext and ciphertext from plain text.
So mathematically or algebraically, how can you
Yes, sir.
connect with this cryptography and algebra.
Okay, cryptography and algebra. Okay, sir. So, to design crypto systems, to design secure crypto systems, we have to choose some secure hard mathematical problems. Hard in the sense, if we are using many computer powers or manpower, it is even then many too much hard to compute to solve. Because suppose it is easy to solve, anyone can break the crypto system. Okay, so to design secure crypto system, we will require hard mathematical problems like integer factorization problem, discrete log problem. There is one more knapsack problem, and there is many more problems. Lattice based problems are there. Shortest integer problem, smallest integer solution problem, shortest vector problem. Many more problems are there, but the difference is integer factorization, discrete log problems that are used in classical crypto systems.
Okay.
These are broken by the quantum computers, and lattices are still secure. So just the relation is you have to find a hard mathematical problem, and by using that, you will use that hard mathematical problem into your design. To get plain text from ciphertext, you will have to solve that hard mathematical problem. Before uh, solving that hard mathematical problem, you cannot get your original plain text. In that sense, we call it secure.
Okay. Thank you.
Okay, sir.
Actually, madam,
Yes, sir.
we can have our own crypto system, whether it is a Caesar cipher, or it is a block cipher, or else any key you generate. You can use congruence modulo, and you can use Euler pi function. That's all right. You can have your own crypto system. What is
Yes, sir.
more interesting here is how to hack a crypto system.
Sir, again, pardon, please.
How to hack a crypto system.
Okay, sir. How to hack a crypto
Yes,
system?
also.
Sir,
Crypto
for
system. Because
hacking crypto
that
system,
will
you
be
yeah.
that will be more interesting and more promising.
Okay,
And
sir.
then
Hacking is a branch. We can say hacking is for computer scientists, and I can just say only if you are able to solve that hardness, you are able to break that hardness, you can hack that system. For example, we
because
are using shift cipher, for example.
mm,
Okay,
mm,
and
mm.
I know you are using the key 7. You are shifting letters by 7 positions. So I'll just simply I get back by 7 positions. I will get your original text. Suppose you are doing emails to anyone, and if anyone is having your password, he can get your data. If the key main is decryption key, main is secret key. If someone is having secret key, if someone is stealing your secret key, he can get your data, he can hack your system.
Okay, actually, why I am asking this, because these BTech guys, in our
Yes,
college, these
yes, sir.
BTech guys, they are breaking the, I mean, Caesar ciphers.
Okay,
They are developing a pseudocode. They are developing a program to break Caesar ciphers. Even
yes, sir.
affine ciphers also.
Okay.
Affine ciphers also, it is easy to break. Whereas your RSA algorithm, DSA
O-
algorithm,
Obviously,
it
sir,
is
it's easy. Yes, shift cipher, a fine cipher are easy to break because
easy.
the key space is only 0 to 26. So
Exactly.
you can always perform a brute force attack. That means you can try all the possibilities, and obviously one possibility is always there.
Mhm.
If Caesar
Actually,
cipher, if shift cipher or a fine cipher is there.
actually, in RSA algorithm also, if you are choosing P and Q to be very large prime numbers,
Okay,
in
sir.
that case, if you are taking M equal to P into Q, then you are finding out phi of N, the Euler value of N. So
Okay.
in that case also, don't you think this calculating this phi of N is also another mathematics, another task, isn't it? Very difficult to
Yes.
find it out.
Yes, sir. Very
And
difficult.
I suppose that in phi of N is taken as a key in algorithm. I don't remember, but anyway,
Yes,
nice talk.
sir. There is a yes, sir. There is a institution like NIST.
Ah,
So there is a reward by this institute if he can break 1024 bits integer.
Oh, Baba. Mm-hmm.
509 digit integer.
Okay, okay. Because these numbers, if you write down, they are very lengthy. Say, if I take a number, say 2 to the power 1024, then if you write it down in
Yes,
a row, it will be of 1 kilometer length. Very difficult
yes, sir.
to, very
So
difficult
that's
to.
why we use that's why we use supercomputers, super computers. Even
Otherwise,
then, these are hard.
yeah, yeah, yeah. Not possible in normal computers.
No, sir, not possible even. Sir,
Okay.
it is possible only in toy examples where we are using three,
Ah,
four, 5 digits number.
for classroom teaching, this will do, isn't it? Because if you take a
Yeah,
small
sir. We
number.
can take always toy examples, but not in the large numbers.
Exactly. Okay,
Yes.
ma'am. Thank you.
Thank you, sir.
So any other questions?
I would
That's a
like to
great.
ask another question, ma'am.
Yeah,
Yes,
yeah.
sir.
According to you, ma'am,
Yes.
which algorithm you feel the most secure for this encryption?
Okay, sir. I can say because I am from post quantum and because Rsa algorithm can be broken by quantum computers. So,
Ah,
in
great.
present time, I think I'll go with NTR crypto system.
Okay.
Yes, sir. Because
You
it is
don't
the
think?
most efficient crypto system. We can use other also, but they are very difficult to implement because they are having large storage complexity, time complexity, computational complexity.
Yes,
That's
yes,
why
yes.
there are many more
Mm,
terms are there to
mm.
define a crypto system. And because I'm having only 45 minutes, that's why I just did not include.
Okay, madam. But you do one thing, madam. My request to you,
Yes, sir.
please send us some papers regarding any crypto system or hacking of a crypto system
Okay, sir.
Yes,
Sure,
sure.
sir.
to our department, so that we will have a discussion on this and
Okay,
let us
sure, sir.
see.
Sure.
Because also people are using probabilities, this
Yes,
random theory and
yes,
all.
yes, sir. Yes,
Yeah. So that would
definitely.
be very fine for us.
Yes, sir.
So,
Definitely, sir.
okay, madam. Thank you.
Thank you so
Okay,
much, sir.
Mantla madam. Over.
Okay, okay. Dr. Singh,
Yes,
just
ma'am.
I want to know how you're putting the strength into your cryptography because hacking is so common nowadays.
Actually, ma'am, we cannot say it's about it's like hacking because cryptography is about designing the systems, and hacking
Okay.
is something different. Yeah, ma'am. Hacking is
Oh, yeah.
a computer
Mm,
scientist can do hacking because he knows all programming, codings also, and in
mm,
because of mathematical background, I can just design. I can just do mathematical modeling. So the
yeah, yeah.
implementation part or hacking part is for computer scientists.
Oh, yeah, yeah. Okay. It's a very nice presentation and nice interaction session also. So thank you, Dr. Sonika Singh. Dr. Abhijit, you for your vote of thanks from our department.
Dr. Abhijit is not audible? Not audible?
Yes, sir, audible.
Uh,
Dr. Abhijit, you
yeah,
unmute.
yeah.
Yeah.
I forgot to unmute. Sorry. So at the end of the 8th Siksha Anusandhan weekly academic lecture, I, Dr. Ravi Sutudar, the co-convener of this weekly webinar series from the Center for Applied Mathematics and Computing, shall take a liberty of proposing the vote of thanks. So we thank the speaker, Dr. Sonika Singh, whose talk has surely helped us to expound our knowledge on uh, in encryption system and its security and applications of uh, mathematics in the encryption systems. Our thanks are due to the colleagues, research scholars, and students in the audience. And our big thanks goes to Dr. Manoj Ranjan Nayak, our Honorable President of SOA, deemed to be university, who has been always been a source of inspiration to all of us. I extend our thanks to Professor Manjulo Das, our head of the Center for Applied Mathematics and Computing, for the necessary supports, and Dr. Atul Kumar Roy, for connecting with the speaker, Dr. Singh. Lastly, on behalf of Center for Applied Mathematics and Computing, Siksha Anusandhan University, extend our heartfelt thanks to all.
Thank you,
So
sir.
thank you, ma'am, once again for this wonderful lecture.
Thank you, sir. Thank you, ma'am. It's my
Thank you.
So, yeah, so I officially end the meeting here.
Yeah.
Stopping the recording. Thank you once again to all.
thank you.